Now you will cover the decoders. As we know that the segmentation model follows the encoder and decoder architecture. So previously we have seen different encoders. Now let's start with the decoders. Decoder basically upsample the input feature map obtained from the encoder. So now we will cover the different decoders to perform the segmentation. These decoders are available in the segmentation models PyTorch or SMP library. The first decoder is the PSPNet or Pyramid Scene Parsing Network. Here is the architecture overview of the PSPNet or Pyramid Scene Parsing Network. In this PSPNet architecture, here you can see the encoder part. So let's represent it with E. So this is the encoder part of the PSPNet architecture in the purple box. So PSPNet architecture basically using the ResNet encoder. Now you can see the decoder part in the red box. So this is the decoder part of the PSPNet architectures. So let's represent it with D. So with PSPNet decoder you can use whatever encoder you want, as we have previously seen different encoders in the SMP library. We will also see how can we use different encoders with different decoders. PSPNet is a fully convolution neural network for image semantic segmentation. It consists of a pyramid pooling module to exploit the local and global context information. PSPNet performs the segmentation on Pascal and Cityscape's benchmark datasets. In PSPNet, first a feature map is extracted from the last convolutional layer of the convolution neural network that is fed to the pyramid pooling module in order to harvest different pooling pyramids. Finally, convolutional layer is applied to obtain the pixel-wise prediction. So consider this input image. First, a CNN is used to get the feature map of the last convolution layer. This CNN architecture can be a ResNet or VGG that can be used to get the feature map of the last convolution layer. Then you can see the pyramid pooling module. This pyramid parsing module is applied to harvest different subregion representations followed by upsampling and concatenation layers to form a final feature representation. Here you can see the different subregions that are obtained after applying the pooling layer, and then upsampling and concatenation layers are applied to get the final features. Finally, the features are fed into a convolution layer to get the final pixel-wise prediction. Here you can see the convolution layer is applied. The pyramid pooling module fuses features under 4 different pyramid scales. The coarsest level highlighted in red is global pooling to generate a single bin output. Then the following pyramid level separates the feature map into different subregions and forms a pooled representation for different locations. The output of different levels in the pyramid pooling module contains the feature map with varied sizes. To maintain the weight of global feature, they use 1x1 convolution layer after each pyramid level. To reduce the dimension of context information to 1 by n of the original one, then directly upsample the low dimensional feature maps to get the same size feature as the original feature map via bilinear interpolation. Finally, different levels of features are concatenated as the final pyramid pooling global feature. Note that the number of pyramid levels and size of each level can be modified. They are related to the size of the feature map that is fed into the pyramid pooling layer. The structure abstracts different subregions by adopting various size pooling kernels in a few strides. Thus, the multi-stage kernel should maintain a reasonable gap in representation. The pyramid pooling module is a 4-level with bin sizes of 1x1, 2x2, 3x3 and 6x6 respectively. For the pooling operation, you can perform the max pooling or the average pooling. Second decoder is PAN or Pyramid Attention Network. So here is the overview of the full PAN or Pyramid Attention architecture with encoder and decoder. So here is the encoder part in the PAN architecture. Here you can see in the purple box. Let's represent it with E as its encoder. So PAN architecture is also using the pre-trained ResNet architecture in the encoder part. And here is the decoder part of the PAN. Here you can see in the red box. Let's represent it with the D as it's a decoder. Pyramid Attention Network is proposed for semantic segmentation. It consists of feature pyramid attention module and global attention upsample module. Segmentation experiments using PAN are performed on Pascal and Cityscape benchmark datasets. Feature pyramid attention module performs spatial pyramid attention structure on high-level output and combine global pooling to learn a better feature representation. and global attention upsample module on each decoder layer to provide global context as a guidance of low-level features to select category localization details. Here you can see the input image, and then the RaceNet is used to extract the dense features. After that, GAU and FPA module is applied, where GAU is Global Attention Upsample module and FPA is Feature Pyramid Attention module. FPA and GAU is used to extract precise pixel prediction and localization details. In this architecture, blue lines represent the downsampling and red lines represent the upsampling. And finally, you can see the output segmentation map of the input image. And third decoder is mainnet, and then linknet, deep lab version 3, deep lab version 3 plus, FPN. So all these decoders are available in the SMP library. When we will define the segmentation model, we will see the architecture of these decoders. And finally, the UNet and UNet++, that is the extended version of the UNet. Here is the overview of the UNet architecture. So here you can see the encoder part in the purple box. So here is the encoder. Let's represent it with E. And then you can see the decoder part in the red box. Let's represent it with D. UNet is a fully convolutional neural network for image semantic segmentation. It is used for biomedical image segmentation. UNet is proposed to perform the segmentation on ISBI cell tracking challenge dataset. It comprised of a contracting path that follow the same fashion as typical architecture of a convolutional network and expansive path that is used for upsampling of the feature map. UNet won the ISBI challenge 2015 for segmentation of neuronal structures in electron microscopic stacks. As you can observe, it's U-shaped, so that is why its name is UNet architecture. On the left hand side, it's a contracting path, and on the right hand side, it's expansive path. Each blue box corresponds to a multi-channel feature map. Here you can see the blue boxes. The number of channels is denoted on the top of the box. The XY size is provided at the lower left edge of the box. White boxes represent copied feature maps. So here you can see the white boxes. So they are the copied feature map. The arrows denote the different operations. For example, here you can see the arrows with the different operations. So blue arrow represent the convolution 3x3 with ReLU. For example, in the start you can see the input image, and then you can see the blue arrow. It's mean 3x3 convolution with ReLU is applied over here. For all the blue arrows in this architecture, convolution 3x3 and ReLU operation is performed. White arrow mean copy and crop. So here you can see the white arrow, so it's mean copy and crop. Red arrow mean max pooling 2x2. So here you can see the red arrow, it means max pooling is applied with 2x2 filter. Green arrow means up convolution with 2x2 filter. So on the right side of the network, that is the expansive path, you can see the green arrow, so it's mean up convolution operation is applied over here. And the last arrow is convolution with 1x1 filter. So in the architecture, before the output segmentation map, you can see this arrow, so it means 1x1 convolution operation is performed over here. So the UNet architecture consists of a contracting path on the left side and an expansive path right side. The contracting path follows the typical architecture of a convolutional network. It consists of a repeated application of two 3x3 convolutions, each followed by a rectified linear unit ReLU and a 2x2 max pooling operation with stride 2 for downsampling. For each downsampling step, double the number of feature channels. Every step in the expansive path consists of an upsampling of the feature map followed by 2x2 up convolution that halves the number of feature channels, a concatenation with the corresponding cropped feature map from the contracting path, and two 3x3 convolutions, each followed by a ReLU. The cropping is necessary due to the loss of the border pixels in every convolution. At the final layer, 1x1 convolution is used to map each 64 component feature vector to the desired number of classes. In total, the network has 23 convolution layers. UNet architecture is using its unproposed or undefined encoder and decoder architecture. But when we will define the segmentation model using SMP library, we will use different encoders with the UNet decoders. So we have seen different encoders and decoders. So in the next lecture, we are going to use these encoders and decoders to define a segmentation model so that we can perform the segmentation. See you in the next lecture.